All right, great to be here. This is going to be somewhat of a shift in gear, so put your PLDI hats on. All right, yes, I'm Matin. I'm going to be talking about this design for doing high throughput Gibbs sampling on GPUs. It's work done with Martin Rinard and Vikash Mansinghka at MIT. It focuses on Gibbs sampling. Gibbs sampling is a fundamental algorithm in probabilistic inference. It's an approximate sampling algorithm, and it has many applications in artificial intelligence, data science, bioinformatics, and many more fields. In fact, to the best of my knowledge, the first ever probabilistic programming language, Bugs, was introduced more than 30 years ago to do this, Gibbs sampling. And it's still somewhat maintained. And the latest version, I think, came out in 2020. Even though it's really popular, Gibbs sampling can only be done in like a limited class of models. It can be only done in Bayes nets whose variables satisfy certain conjugacy relationships, and we'll see why. But even then, it's very useful. I'm going to try to show that even for this very limited class of models, doing a good job of having a high throughput sampler on the GPU could still be kind of nuanced. But we first need to know what the challenges are and what the solutions are. So let's do a quick run through of Gibbs sampling. In this talk, I'm going to use this factor graph notation to denote graphical models, to show graphical models. A factor graph is just a graph with two types of nodes, variable nodes and factor nodes. And variable nodes we show with circles, factor nodes we show with squares. And the graph is bipartite. Circles only connect to squares and vice versa. The graph as a whole just represents a real valued function. The inputs to the function correspond to like these variable nodes. And they could essentially take arbitrary type. Here I've shown one with like 5 inputs. And they could all have a different type. And the function we assume factorizes into a product. And each factor in the product corresponds to a factor node in the graph. And the adjacency relationship in the graph denotes what variables participate in what factors. So here, for example, we can see that factor f6 contains variables x5 and x4 by just looking at the graph. OK, so how do we actually do Gibbs sampling in this notation? Well, we first start by assigning arbitrary values to the variables. Some arbitrary values have been assigned. And then we go over the variables in some order. So here I've started with like x1 as my first variable. What we do here is we fix all the other variables to the values that they have currently and resample x1 from a distribution whose density corresponds to like, the full density of the graph, but partially evaluated at everything else fixed. And we call this the Gibbs sampling distribution of x1. And here I've put it on this slide. OK, once we've done this, we're going to go to the next variable, for example, x2 here, do the same exact thing for x2, sample it from a Gibbs sampling distribution by fixing everything else, then x3, and so on. And once we do this for all the variables once, this is called a Gibbs sweep. And as we do many Gibbs sweeps, the joint sample here, the sample of x1 through x5, converges in distribution to the normalized density denoted by the whole model. OK. So one crucial thing to note here is that the Gibbs sampling distribution of each variable only depends on a subset of the entire set of variables. And the subset is the ones that participate in the factors that the variable under consideration participates in. So for example, here for x4, we can see that if we write out the densities, the Gibbs sampling distribution of x4 only depends on x3 and x5 because it participates in factors f5 and f6, which are all the factors that x4 participates in. And this set of distributions, this set of variables, the set of variables that fully determine the Gibbs sampling distribution of a variable under consideration is called this Markov blanket. And here I've put it in blue, for example, for x4. OK, so just to summarize, how do we do Gibbs sampling? We have a bunch of sweeps we need to do. For each one of the sweeps, we go over the variables. We first go gather the values of the variable under consideration, of the variables of the Markov blanket of the variable under consideration. We then partially evaluate all the factors that contain the variable, multiply them together, and we resample the value of the variable that we are considering by just normalizing that and sampling from it. And this, being able to go to this normalized product is why we need conjugacy relationships. OK, I'm going to refer to these 3 stages at the inner loop of Gibbs sampling as the gather stage, the aggregate stage, and the sample stage. And we're going to use this terminology. OK, so So this brings us to the first big idea behind the design, is that if the Gibbs distribution of a variable only depends on the Markov blanket of that variable, then if two variables have disjoint Markov blankets, they could be sampled in parallel. And this is a well-known idea. It leads to this algorithm called chromatic Gibbs sampling. And chromatic is there because you do a graph coloring at some point. And to do that, you just create a simpler graph from the factor graph called the Markov random field graph by connecting any two circles that have a square neighbor. And by construction in this graph, two nodes are adjacent if and only if they participate in each other's Markov blankets. And so if I color this graph, do a vertex coloring of this graph, I get a partitioning of the variables into sets that each color can be sampled in parallel, essentially. All right, now we have the second observation, which is this is not enough if you want to do high throughput Gibbs sampling on a GPU. And to see why, I'm going to show you two kind of representative examples of the workloads that people use for Gibbs sampling. The first one is this friendly Ising model. If you look at it, you see that the factor graph for an Ising model is highly regular. And the Markov blanket of each variable is the same size and it's very small. So the sensible way to write a high throughput Gibbs sampler for this type of a model on the GPU is to just parallelize over the sets of variables that have disjoint Markov blankets, but then for each one of the variables, just serially do all the three stages and do the resampling. Now let's contrast that to this Bayesian mixture modeling kind of factor graph. Let's assume a Gaussian mixture model. You can see that this is a highly irregular graph. And the reason for that is typically in a mixture modeling problem, you have many more data points than you have mixture components. That's kind of the point of mixture modeling. And so if you wanted to do implement a high throughput version of this on the GPU, for these variables down here, for the variables that indicate what data point goes to what mixture, you would do the same as before. These have almost all the same degree and a small Markov blanket. So you do that part in serial. You parallelize over them, but for each one of the stages of the Gibbs sampling, you do them serially. But for the variables on the top, the ones that show the mixture component parameters, what you would want to do is you want to do the aggregation step in parallel as well. Because otherwise, you're leaving throughput on the table. And so that brings us to the last big observation behind the design, is that because the parallelism will depend on the workload under consideration, you want it to be programmable. And so this makes our design very similar to languages like TVM or Halide, where a program doesn't only specify what computation needs to be done, but also at a high level of abstraction says, how should it be parallelized? And this is going to be the full design then. We start with a user-facing kind of BaseNet DSL. We lower it to a factor IR, which kind of lets us, the same way factor graph lets us read the factorization structure really easily. That allows us to do the same. And then using that, we could detect parallelism over variables using chromatic type techniques, or detect parallelism where parallelism can happen for aggregation. All of that is indicated in a schedule object. The schedule object could be tuned using dynamic analyses optionally, and then we use that finally to generate the final GPU code. And there's tons of details that go into this. I'm not going to go over the details. I'm going to do a shameless plug. Come to the poster and talk to me. I'd be excited to talk to you about it. The only thing I will briefly mention is the schedule object, partially because my review said that would be a good thing to talk about. The schedule object is a simple type of data structure. It has a bi-level hierarchy. The first level of the hierarchy we call steps, and that just says what groups of variables should be sampled before the others. So even in the chromatic case, you can think about each color is sampled in parallel, but the colors themselves are serialized. And so that's the first level of the scheduled data structure. The second level of the hierarchy is what we call streams. And streams indicate within each step what variables generate independent streams of instructions to be executed on the device. And essentially, this is just to accommodate the hardware. Lastly, we could tag some of these streams for whether the aggregation step should be done in parallel or serially. And with this sort of a scheduled data structure, we can write high throughput samplers for both the Ising example, for the mixture modeling example, and many more things. All right, that's all I had. Thank you for your attention.
Great. Time for a question or two. Yeah, thanks. Maybe I missed the point entirely, but the
the schedule object, the goal is really for the user to interact with them. It's not because some part of it presumably is automatically generated by some chromatic.
Exactly. So the schedule object has essentially 2 points. One of it is like, if the user knows what to put in, it could partially put that in, and the rest is filled out by this chromatic thing, and etc. But also, once you have a reified schedule object, you could search over the space of schedules and do auto-tuning and dynamic analyses to like get even better performance based on the workload itself. Yeah.
Thanks.
Sure.
Maybe I'll ask a quick question while we get the next speaker, Karen, to come up. So do you know if there's been work on sort of like optimal chromatic or like what makes a coloring good for a chromatic Gibbs? And do you think, all of these other sort of fine-grained options in the schedule changes that at all?
Right. So the thing you want in the coloring is to have as few colors as possible, because colors kind of correspond to the serial stages. But graph coloring is like NP complete or NP hard or one of those. So I have some like experimental results there. I don't know if there's work on like optimal coloring, but I just use like a run-of-the-mill greedy coloring algorithm, and for like the typical benchmarks that people use and a bunch of like useful classes of models, I got small numbers of colors, so I'm happy. All right, thank you.